A volunteer stands over a bucket, holding a measuring cup of concentrated liquid fertilizer. They pour it in, eyeball the mixture, and hope they have the ratios right. For a local farm, this quiet, mundane moment is exactly where things start to go wrong. Community-driven agriculture relies on neighborhoods coming together to secure their own local food sources. When it works, it creates shared green spaces that cycle nutrients back into the soil and preserve local biodiversity. But their day-to-day survival hinges on a highly variable resource: unpredictable volunteer labor. On any given Tuesday, the person watering the crops might be a master gardener or a high school student who has never grown a tomato. As volunteers cycle in and out with different backgrounds, crop care changes with them. Without a centralized tracking method, the farm cannot ensure the same quality of care from day to day, leading directly to inconsistent operations. This flowchart traces the consequences. Step 1, manual judgment, leads directly to Step 2, inconsistent, unbalanced fertilizer ratios. From there, improperly mixed solutions result in Step 3, severe nutrient wastage that drains budgets. Ultimately, this chain reaction ends at Step 4, decimating overall crop yields. This comparison table isolates the vulnerability. As long as nutrient preparation sits in the manual mixing column, dependent on individual knowledge and visual guesswork, the farm is operating at a high risk of resource drain. Securing the yield of a community garden requires taking the chemistry out of human hands. The survival of the farm depends on standardizing the nutrient cycle entirely. To sever this chain of human error, researchers at University Technology Mara developed the IoT-NMD, an automated internet-connected fertilizer mixing and dispensing system designed specifically for shared agriculture. Looking at the smart dispensing sequence, the process begins digitally. An IoT microcontroller receives a command for a specific pre-programmed crop recipe, completely bypassing any need for human estimation. This schematic outlines the architecture. A multi-tank design strictly separates pure liquid concentrates in the upper tanks from the centralized mixing vessel below. Precision solenoid valves and automated pumps release the exact required ratios of water and chemicals directly into the tank. By delegating the physical labor to an automated architecture, the farm no longer suffers when volunteer schedules conflict. The exact right mixture is prepared, exactly when the crops need it, regardless of who is working that day. But mixing the liquids is only half the battle. Before a single drop touches a plant, the system acts as a digital gatekeeper, using a suite of integrated sensors to interrogate the solution. Inside the tank's verification loop, sensors monitor liquid levels, pH, and electrical conductivity to confirm the exact nutrient concentration. If readings miss the target, the quality gate triggers an automated redose protocol to fix the imbalance. Only after the solution passes this strict chemical audit is it finally cleared for Step 4, flowing out into the garden to feed the crops. This closed-loop verification guarantees optimal chemical balance every single time. It turns an environment built on guesswork into one governed by mathematics. To test this in reality, the prototype was deployed here at the Taman Mawar Community Garden in Johor, Malaysia, a live, active urban agriculture site run entirely by volunteers. Operational data from the deployment revealed an immediate drop in nutrient wastage. By eliminating manual preparation, the farm secured standardized fertilizer quality across crop cycles. Secondly, by handling precision chemistry, the system reduced the need for physical supervision, directly improving the volunteer experience. This technology removes the barrier of specialized agricultural knowledge from the volunteer experience. It automates the precision chemistry in the background, allowing the community to focus their time on physical cultivation and plant care that machines cannot replicate. This connectivity diagram shows how operational oversight goes mobile. The system sends real-time data straight to a digital dashboard, allowing volunteers to remotely monitor water and nutrient levels. That same dashboard maintains a transparent record of fertilizer consumption, guaranteeing equitable resource management across all growing zones. As this framework outlines, this low-cost hardware isn't limited to a single neighborhood garden. It is a proven, scalable model ready to support educational agriculture in schools and commercial microfarming in urban centers. Achieving local food security doesn't require expecting amateur volunteers to work like chemical engineers. By establishing a single source of automated data transparency, communities can finally protect their resources, support their workers, and guarantee a thriving harvest.